few. So let's review what a few words mean and really let it sink in. Because honestly, this is what used to confuse me, was the wording of what I was learning. So we know roots mean solutions or zeros or where it crosses the x-axis, right, everybody? Most of the time. There are roots that don't cross the x-axis, but roots are the solutions of a polynomial. Now there are real roots. If we have a real root, it is absolutely true that it will cross the x-axis because right here is the real number line. So real roots have to cross the x-axis. Now real roots could be, they could cross the x-axis like a 2, like a whole number, or it could be irrational, like 2 root 3, for example. Those are both real roots. They both cross the x-axis. One is rational, one is irrational. Okay, imaginary roots do not cross the x-axis. So this is when we have imaginary solutions like 2i and negative 2i. So, I'm going to ask you a question real quick. If I told you that I have a degree 4, but it only has 2 real roots, it only crosses the x-axis in 2 places, what would you know for sure? 2 of them are imaginary because they do not cross. Okay, good. Now rational. The word rational means something that can be written as a fraction. So these are all rational numbers right here. 1/6, 2/3, 3, and negative 5. Because they're all technically can be written as a fraction. Rational roots. So let's say these are solutions. These would be called rational solutions, rational roots. Because they're solutions that can be written as a fraction. Does everybody understand? Okay, cool. Alright, so here's another thing to note. Understanding this is key. If we have a polynomial that can be factored, if we can factor it like we saw in the last unit, then this is always going to be true. If a polynomial is factorable, we will have rational roots, like 2, 1/2, negative 2/3, because if it's factorable, we're able to find these fractional solutions. Does everybody understand why? Now what if it's not factorable? That's when we get irrational roots, such as 2 root 3 and negative 2 root 3, or imaginary roots, 2 minus I and 2 plus I. But if it is factorable, you will be able to have fractional solutions. Are we good? Okay, awesome. Now we can start learning the rational root theorem. Okay, so this is 1-7. Alright, so now here's the thing, guys. We're going to have polynomials that don't factor, and they're big, huge, and nasty. So it says, when we have huge polynomials with a leading term and an ending term that have a ton of factors, it makes it very hard to factor. So I just want you to look down here. If I said find the solutions of this big, nasty polynomial, it looks nasty, and we wouldn't even know where to start as of now. There's no factoring method we've learned so far. Well, to make it worse, if I made the leading term be like 24, and the ending term be like 27, now it's even worse. These are huge leading coefficients of a big thing. That's going to make it really hard to factor. So now, we don't know how to factor it, in fact. That's going to make it really hard to solve. So now it says right here, factoring a polynomial, when we have the polynomial, this huge polynomial, it's just saying if we have this polynomial, a sub n, x to the n, plus all this stuff, plus a sub naught. It says it can be challenging to factor that, especially when the leading term and the ending term have many factors. The factors of a number a sub n and a sub 0 in p of x can help you factor a polynomial and solve the equation when we set it equal to 0. So it says right here, one way to find the solutions of a polynomial when we set the polynomial equal to 0 is to guess and check. So let's look right down here. If I said to you, solve this, you're not allowed to touch a calculator, guess and check. What would you do? Synthetic division, wouldn't you? And see if the remainder is 0. But how, like, where do we begin? Isn't there an infinite number of solutions we could be guessing and checking? Yes. Well, then you'd be here all day. That is not an effective way to solve. But now what if I gave you a way to narrow down the things you guess and check? Then it might not be so bad, right? So that's what the rational root theorem is. It's a way to narrow down the possible solutions. So everybody, right here is what we're going to be writing down. So here's the rational root theorem. It says let p of x, this just means a polynomial, with a sub n, x to the n, there's our leading term, plus all this stuff, plus a sub 0. That's our constant. It says let the polynomial with integer coefficients, that means whole number coefficients, there are going to be a limited number of possible roots when the polynomial is set equal to 0. Now this is always going to be true. Here's our first thing. It says integer roots or whole number solutions must be a factor of a sub naught. So that's maybe the first thing you should write down. That will be true. Everybody, I'm going to say that again. Whole number solutions will be factors of our a sub naught, which is our constant. That will always be true. So for example, look at this. 21x squared plus 29x plus 10 equals 0. If we were using this idea, this would be true. So right here is our constant, right? Any whole number solutions that this polynomial will have to be factors of 10. So factors of 10 are plus and minus 1, plus and minus 2, plus and minus 5, plus and minus 10. You guys, if this polynomial has a whole number solution, it will be one of these values. Period, end of story. So do you see how that's a lot less? Guess and check. Still kind of a lot, but it's a lot less. Now this is also true. Second thing. So that was our first thing. Second thing is, it says rational roots must have, so this means fractional, not whole number, but fractional roots will have reduced form p over q, where p is the integer factor of the constant, and q is the integer factors of a sub n. So let me just state this a little bit more simpler. Okay, you're going to call p your constant in your polynomial, always. You're going to call q your leading term, your leading coefficient. So p is 10, and q in this example is 21. Does everybody understand where I'm getting p and q? That's just something you're always going to do. P will always be the constant, q will always be the leading term. So now any fractional solutions will be any p over q. It's going to be all p's divided by all q's. So we've got to list out the factors of all of our p's and then divide it by all the factors of q. So what are my factors of p? So what are my factors of 10? 1, 2, 5, and 10. Now we don't know if they're positive or negative, so it could be plus or minus, we don't know. It could be any of those. So there's our possible p's. Now our possible q's, any factors of 21, plus and minus 1, plus and minus 3, plus and minus 7, true? Plus and minus 21. So now the only fractional solutions that polynomial could have is any p divided by any q. So p divided by q. So I've got to do all p's divided by all q's. 1 divided by 1 is 1. 1 divided by 3 is 1/3. 1 divided by 7 is 1/7. 1 divided by 21 is 1 over 21. I think that you should probably not write this one down. Just get the idea, and then we'll do a better example that's not so huge. You guys see where I got all those values? So we don't know if it's plus or minus. So I'm going to put commas in. Okay, those are the possible, that p divided by all the q's. Now p divided by q here. 2 divided by 1 is 2. 2 divided by 3, 2/3. 2 divided by 7, 2/7 is a possibility, and 2 divided by 21. These are possible rational roots. Do you see other fractions? They're rational roots. These are possible rational roots. Now 5 divided by 1. 5/3, 5/7, and 5 over 21. And then we're almost there. 10 plus or minus 10, plus and minus 10/3, plus and minus 10/7, plus and minus 10 over 21. Guys, these are the only possible rational solutions of that polynomial. So, there's a lot. In fact, that's a lot. But it's a lot less than infinite, right? Still not the best, but still better than infinite. So guys, if it has a fractional solution, it will be in this. It will be one of these, if it has fractional solutions. So, yeah. Pretty cool, right? So this one's huge, and then we could test all of them by synthetic division. If we get a remainder of 0, we know it's a root. If not, it's not. But that would be how many solutions? 1, 2, 3, 4. 4 times 2, right? Because there's 2 here. So 8. And then we have to go down 8 times 1, 2, 3, 4. So we would be testing a lot of values here. So, it's helpful, not foolproof. Okay, let's do one that's not so nasty. So right here, it says, what are the rational roots? So let's list out the possible rational roots, and then let's do synthetic division to test. So you'd say, okay, the possible rational roots are some p divided by q. So now you have to remember, p is the constant, q is the leading coefficient. So what I do is go down here and list out all the factors of p. So factors of 5, plus and minus 1, plus and minus 5. Do you see how that's a lot less? This one's a lot more reasonable. Q, all the factors of q, plus and minus 1, plus and minus 2. So now any p over q are possible solutions. So let's do 1 over 1, so p divided by q. So plus or minus 1 could be a solution. Now you got to do p divided by q here, so 1/2. So plus or minus 1/2 could be a solution. I've taken care of 1. 5 divided by 1 is 5, and then 5 divided by 2. So guys, this one is not bad. These are the possible rational solutions. There will not be a rational solution, not in this set for this polynomial. It has to be one of those. So that's not bad. So now what we would do is just start testing. So let's do synthetic division. Let's just start with 1. So here we go. Put in a 2, a negative 1, a 2, a 5. We drop straight down. 2 times 1 is 2, right? Add straight down, we get a 1. 1 times 1 is 1. Add straight down, we get 3. 3 times 1 is 3. Add straight down, we get a 8. There's our remainder, so 1 is not a solution. Let's try negative 1. Here we go. 2, negative 1, 2, 5. Drop straight down. 2 times negative 1, negative 2. Add straight down, we get negative 3. Negative 3 times 1 is 3. Add straight down, we get 5. 5 times negative 1 is negative 5. Add straight down, we get 0. So now find a special place to put your final answer. So I'm going to put my final answer in this box. We just found that x equals negative 1 is one of our rational roots. Now we know there are 3 total solutions. We don't know, though, if the other 2 are irrational, imaginary, or both rational, right? There are 2 other solutions. So what we are going to do is we're not going to keep testing. This is not a good method. It's because just don't. From here, use your knowledge to do it easier. So watch what I would think. Here's how I would think through it. Didn't we just take a polynomial of degree 3? We divided it, so won't we have a degree 2? So let's look at our new polynomial. We have a 2x squared minus 3x plus 5, don't we? So now think about it. If this quadratic factors, we're going to have 2 more rational roots, aren't we? If it does not factor, I would have to use quadratic formula. Wouldn't that be imaginary and irrational roots? Yes, that's the definition of why we have to use the quadratic formula. Now it says, what are the rational roots? So if we need the quadratic formula, we're done. This is the only rational root. Does that make sense? If it does factor, factor it and use that to find the other 2. Okay, let's see if it factors. We got tricked first hour. Well, multiplies to be 10 and adds up to be negative 3. We went like this. 5 times 2, and then we went negative.
Wrong.
Wrong, because it doesn't work in this box. It works over here, but not over here. So it does not factor. So we would need the quadratic formula. It didn't say find all the solutions. It only wants rational solutions. So we're done. Negative 1 is the only one. Does that make sense? Okay. If it did factor, I would factor it and then write down the other 2. Okay, let's go on to another one. This is number 4 off the homework. So you're getting 1 off the homework done. Here we go. If I said find all the rational roots, we'd first list out possible rational roots. Yes. Uh-huh. This one? Okay.
Can't you just put the first 2,
Should I erase the 7 and the 4?
it doesn't matter.
Okay.
Can you just put these in parentheses, then this in parentheses, then this in parentheses, and solve it like that? Or
Good question. No, because then what would you do? Because it's not factoring by grouping, right?
why isn't it?
Because they're not the same inside.
Okay.
And then factoring by grouping only works with 4 terms. Valid question, though.
Okay.
Yeah, so valid question. There's no factoring method that we've learned so far that this would factor with. Yeah, good question. Okay, let's do number 4. So we're going to have to list out the possible rational roots. So remember, everyone always likes to do this. This is where people mess up because P comes first in the alphabet, so they want to put P here, but it's backwards. Here's P, here's Q. So P is the constant, Q is the leading term coefficient. Here we go. List out all the factors. So we're going to be doing P over Q here in a second. Let's list out all the factors of P, not including the negative because we're going to put the plus or minuses right here. So factors of 4, plus or minus 1, plus or minus 2, plus or minus 4, correct? Those are all the factors of P. Now let's list out all the factors of Q. Plus or minus 1, 12 has a lot, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus and minus 12. Now we have to do all P's over all Q's, which is not pretty. There's going to be a lot, but that's going to be okay. So 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4, 1 divided by 6, 1 divided by 12. Write them all down. So we have plus or minus 1, 1/3, plus or minus 1/3, plus or minus 1/2 I missed, plus or minus 1/4, plus or minus 1/6, plus and minus 1/12. Those are possible rational roots. Yikes, that's a lot. That was just 1. Now 2 over 1, so plus or minus 2. True? Now look, 2 over 2 is 1. You don't need to list it out again. We've already got 1. 2/3, we don't have that one, so we need plus or minus 2/3. 2/4 is a half. We've already listed that. 2/6 is a third. We've already listed that. 2/12 is 1/6, and we've already listed that. We just took care of 2. P over Q, so we have plus or minus 4 over 1, which is 4. 4/2, which is 2. We've already got it. 4/3, we don't have that one listed. Then 4/6 is 2/3, we've got it. And then 4/12 is 1/3, we've got it. So guys, if there's a fractional solution, it's going to be one of those. It has to be one of those. So now what would we do? We would start by testing values. Now how many values is there to test in here? A lot. So now you would just have to get going and go for it, and it would take you a minute. So first hour we started going, and we tested, 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 and we tested. And guess what? None of them worked. So what's our answer?
None.
No rational root.
Do you always have to do this one, or can you use factor, not factor, and factor, or is that not rational?
You have, rational means fractional.
Okay.
So you have to have all of the possible fractional roots. So you're saying, can you just use whole numbers? Those are possibilities, but so are these fractions. So you can't stop after whole numbers because those are just fractions like all the rest. Does that make sense? So this one had no rational roots. We tested them all first hour. It took us a while. And there are no rational roots. So what do we know? There are 4 roots. 2 must be, so either they're all imaginary, correct? Or they're all irrational, or we have 2 imaginary, 2 irrational. But that's not what it asks. It says, what are the rational roots? There's no rational roots. Okay. So what I want you to do is problem 1, 3, 5, and 6, and skip 2. So work together. On number 1, you should say, okay, list out the possibilities, and then say, okay, Johnny, you take that 5, and I'll take negative 5, and then we'll test it, and then we'll tell each other. Does that make sense? You can go quicker. Yeah? Find the possible rational roots. Ready, go. This we already know, so we're going to fly through this. So the conjugate root theorem says if we have an imaginary solution or irrational solution, its conjugate must also be a solution. So right here, if x equals 2 minus root 5 is a solution without being told 2 plus root 5 must be a solution. Remember, conjugate just means change of sign in between only. So then if x equals 2 plus I is a solution, 2 minus I must be a solution. Okay, using that knowledge, we're now going to do this. It says write a polynomial with these given roots. You already know how to do this, so you should not need to take notes for this part. So, we have a polynomial with x equals 2. Is its conjugate a solution? No. It's not imaginary. It's not irrational. It is only irrational and imaginary roots. Right, everybody? That's one of the most commonly missed things. It's not just everything gets a conjugate. No. Imaginaries only. And irrationals only. So x equals 2i is a solution. So x equals negative 2i must also be a solution. It wants to know what the polynomial is in standard form. So we work backwards. So we have an x minus 2. We subtract 2i, subtract 2i. So we have an x minus 2i. We add 2i. So now we have an x plus 2i. Now we need to multiply it out. Everyone listen, when you have conjugates, always multiply those together first. So we know when multiplying 3, we multiply 2 together, then multiply in the third. Always multiply conjugates together first. X times x is x squared. With conjugates, we know our middle term cancels out. And then right here, we get minus 4i squared. True. Now hopefully we're at the level where we can just say, so that's x squared plus 4. Do you agree? Now we have x squared plus 4 times x minus 2. So now we would distribute, so we get x cubed plus 4x minus 2x squared, and then minus 8. So our final answer would be written in standard form, x cubed minus 2x squared plus 4x minus 8, right? Okay, awesome. Next one. This is not the homework, number 15. So I would do this one. So it says, write a polynomial with these given solutions. Now notice on the last one, when we had 3 solutions, it came out degree 3, which should happen. So right here we have x equals 3i as a solution without being told what else is a solution. Negative 3i, and if x equals root 6 is a solution, since that's an irrational, we know that negative root 6 is also a solution. There are 4 solutions, therefore it should be degree 4 in the end. So now work backwards, so we'll subtract 3i. So we have x minus 3i. Now we'll add 3i. So we have x plus 3i. Then we would subtract root 6. X minus root 6. Then we'll add root 6. So we have x plus root 6. When multiplying 4 things together, multiply 2 together, then multiply in all of it. So, once again, always multiply your conjugates together. So we would multiply this out, so we would have x squared. The middle term cancels out with a conjugate. So then right now we have minus 9i squared, which simplifies to be x squared plus 9. There's that. Let's go over here. X times x is x squared. We're going to have middle terms cancel out. Then right here, this times this is minus root 36, which is x squared. Good, x squared minus 6. So now we're going to multiply out those. We're almost there. X squared is x to the 4th, minus 6x squared, plus 9x squared, minus 54. Combine like terms and you're done. X to the 4th plus 3x squared minus 54. Now we know how to solve this, don't we? A U substitution. So we could go backwards if we wanted to see if we ended up in the right place. Okay, awesome. Okay, does that make sense? So, awesome. We're going to keep going for a second. We already know how to do that. So, now we're going to learn one last thing. This is the last thing we have to learn today. It's called Decartes' rule of signs. So this is one additional way to determine some more information about our solutions, about our roots. So we just learned that rational roots, the P over Q, are the possible rational roots, which narrows down our possible solutions. Now we can also have this information. So this French mathematician named René Descartes recognized a connection between the solutions of a polynomial equation and the plus and minus signs of the polynomial in standard form. So this dude, clear back in the 1500s, was drawing in the sand with his fingers for days on days and noticed something always happens with polynomials. So if you guys think that your life's hard, he didn't have a calculator. So once again, he was recognized this connection. Now this will always happen. So then he came up with a proof for it, and now it's named after him. So if we have a polynomial in standard form, let me show you. Like for example, x cubed plus x squared minus x minus 5. For example, that's a polynomial in standard form. This is always going to be true. The number of positive real roots when the polynomial is set equal to 0, the number of positive solutions will be equal to the number of sign changes between plus and minus signs. So, right here guys, look. This is the positive x-axis. Do you guys see? We're determining right now how many times it's going to cross the x-axis in the positive x-axis. So we're going to count how many times it changes signs. So from here, it's positive to positive. That did not change. Positive to negative, that just changed. Does everybody agree? Now, negative to negative did not change. So we're done. There was only one sign change. That means there will be one positive real root, for sure. Everybody good? That will happen. So there is one positive real root here, for sure. Now let's talk about negative real roots. So look right here, like for example right here, we're now talking negative x's. So how we determine that is we plug in a negative x, and then we simplify it, and then we count just like we did with the positive. So let's plug in negative x into the original. So that would be negative x cubed plus negative x squared minus negative x minus 5. Now why am I plugging in negative x? Because I want to know the negative x-axis. You guys see? So now let's simplify it, and then we'll count sign changes. So negative x cubed is negative x cubed. Negative x squared is positive x squared. Negative and a negative becomes a positive, and then we have a negative. Minus 5. Okay, so from start to end, let's count how many sign changes we have. Negative to positive, there's 1, right? Positive to positive is all good. Positive to negative, oh, 2. So 2. So there is going to be 2, then it actually goes down in 2s. So there's either 2 or 0 negative real roots. So that's always going to go down in 2s. Now look, the 1 couldn't go, we said there was 1 positive real root, correct? You can't go down in 2s there because 1 minus 2 is negative. That doesn't even make sense, right? So we go down in 2s though. Oops. Okay, so it's either crossing the axis twice in the negatives or 0 times. Okay, so it's helpful somewhat. Okay, so let's answer this question. Let's use that. What does Descartes' rule of signs tell you about the real roots of the polynomial? So let's figure out how many positive real roots we could have and how many negative real roots we could have. So let's start with positive. So you count, for positive, you always count the signs of the original. So here we go. Positive to negative, negative to positive, that was our second one. Yeah? So there is 2 or 0, it goes down in 2s, 2 or 0 positive real roots. So guys, if we were to graph this, it's either going to cross 2 times or 0 times over here. You guys understand? That's the positive x-axis. Okay? Awesome. Let's test out how many negative real roots we have. So to do that, you got to plug in negative x, since we're looking at the negative x-axis. So that's negative x cubed minus negative x squared plus 1. So that's negative x cubed minus x squared, right?
Oh yeah.
Because this becomes positive, minus, and then plus 1. Okay, let's count. Negative to negative, no sign change there. Negative to positive, so there's 1. There is definitely 1 negative real root for 100% sure. So it is definitely crossing the x-axis in the negatives 1 time for sure. Period, end of story. Does everybody understand that? So you see why that might be useful? Because shouldn't we maybe then test negatives first? Because we know for sure it's crossing the negative axis 1 time. You guys see why I would test negatives first? So that's why it's somewhat useful. Now here's the catch. Everyone listen, because I know a lot of you have a misunderstood thing with this. These don't have to be rational. They don't have to be rational. So this could be crossing, but it could be at an irrational number. These aren't rational. Do you guys get what I'm saying? So this actually could be crossing at negative 2 root 3, which wouldn't have been in our solution set. So would that even have been helpful? Not really. So honestly, it's just kind of somewhat helpful. It helps you know where to start testing. But it doesn't make it foolproof. Does that make sense? Because I always have people say to me, well, I know there's 1 negative in this Christensen, but there's not. I just tested. I'm like, yeah, because remember, it could be irrational. They're like, oh, yeah. Okay, let's do some. Let's use it. So look, I graphed that just to show you. That really happened. We said there was 1 negative, which is right there. And then there is 0 positive. There was 2 or 0 possible, it was 0. Okay, here we go. Okay, number 19, it says, what does Decartes' rule of signs say about the number of possible real roots or positive real roots and negative real roots? So let's determine how many positive real roots we could have. So let's count our sign changes. Positive to positive, positive to negative, negative to negative. So there is definitely one positive real root, for sure. That doesn't mean it's rational, but still, that helps us know we should probably test positives first, just because it's possible. There's definitely one. Negative. So negatives, we got to plug in a negative x. So 3 times negative x cubed plus negative x squared minus 8 times negative x minus 12. Simplify it correctly. So this would be negative 3x cubed plus x squared plus 8x minus 12. Then we count our sign changes. Negative to positive, there it happened. Positive to positive, nope. Positive to negative are second. So with negatives, so I'm going to go right here and write it, we have 2 or 0 negative real roots. We just answered the question. Now once again, that's only somewhat useful. I would test positives first, but that doesn't necessarily guarantee that we're going to find one in our rational roots. Okay, so let's do another one off the homework number 23. It says find all the rational roots when the polynomial is set equal to 0. So now that we know both, we're going to use that to determine which one we should test first. Now we know the rational root theorem and Decartes' rule of signs. So here we go. Let's first list out our possible rational roots, p over q. These are the possibilities. So here's our p. Our q is 1. That's good. That makes it really easy. So all the factors of p, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Our q's, plus or minus 1. True? So all p's divided by q's will just be that. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. These are the possible rational roots. Now let's do Decartes' rule of signs real quick to determine if we should test positive numbers or negative numbers first. So let's count for positive real roots. Let's count. Positive to negative, there's one sign change. Negative to positive, 2. So don't we know, and then positive to positive doesn't change. So there can be 2 or 0 real. Positive real. Negative, so how many negatives is there? So negative x cubed minus 5 times negative x squared plus 2 times negative x plus 8. So I get negative x cubed minus 5x squared minus 2x plus 8. So negative to negative, negative to negative, negative to positive. Oh, just one. There's one negative real. So shouldn't we test negatives first? Yes. Okay, let's do. So everybody pick a negative number. Somebody pick negative 1, somebody pick negative 2, somebody pick negative 4, somebody pick negative 8. Let's all split it up, pick a different one, and let's see which one works. There's only one. So if it's any of these, it's only one of those, yes.
So when it says 1, is it down?
Nope, it could be irrational. But that just helps us know we should try testing there. Because what if there is one? What if it is? Does that make sense? Okay, you tested negative 1 and you said negative 1 works. Okay, so let's use some negative 1. So put a special box with your solution. So x equals negative 1. It wants the rational roots. Now what we should be doing now is taking the new quadratic that you just got and seeing if it factors to continue. So what's the new quadratic you got? Plus 8? Okay, let's see if it factors. What multiplies to be 8 adds up to be negative 6. 4 times 2, negative, negative. Does that work? Okay, I can quick factor to x minus 4, x minus 2. Therefore, x equals 4 and x equals 2. There's our other two rational roots. That was way quicker than testing all of them. Yes. So, if it factors, do the factoring thing. Yes. Because we know for a fact there's one negative real root.
Oh, and there's 0.
It could be 2 or 0, so that's a lot more to risk. Okay, all good? Hey, what if this quadratic wouldn't have factored? We would have been done, huh? Because that's the only rational root. Okay, we're getting it. Okay, let's do one more. 25. So let's list out the possible Q over Q's. Factors of P. Q. Factors of P. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Q, plus or minus 1, plus or minus 2. So now start doing P over Q. So we're going to have plus or minus 1, plus or minus 1/2, right? Plus or minus 2, plus or minus 2 over 2 is 1, so we've got that listed. So plus or minus 3, plus or minus 3/2, plus or minus 4. 4 divided by 2 is 2, plus or minus 6, plus or minus 6/2 is 3, plus or minus 12, plus or minus 12 over 2 is 6. Okay, awesome. There's our possible roots. Positive or negative, what should we test first? So Decartes rule of signs really quick. So Decartes rule of signs. So positive, 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 negative. I like it. One only, right? So there's one positive real root. That doesn't mean it's rational though. But it just helps us know where we should probably start testing. So I'm going to start testing. I'm going to just go for it. Do you guys agree? Do I even have to? Okay, let's think. Let's think exactly. Do I even need to plug in negative x at this point? How many degrees is it? 3. So I'm either going to have 2 solutions that are negative real or 0, right? If you don't know that though, just do the math. This is a positive sign. Okay. Okay, awesome. So let's start testing. So everybody, I always start with positive whole numbers and go with those first, test those first. And then if not, then I test the positive fractions. So everybody, actually, let's all just split it up. So everybody pick a positive number. Somebody pick positive 1, somebody pick positive 2, 3. Somebody pick positive 1/2. Somebody pick positive 3/2. Take the hard ones, some of you. 4, 6, and 12. Which one works? Pick one and go for it. You said 4 doesn't? 6 doesn't? 1 doesn't, 3 doesn't. 1/2 works. We're done. We can stop because we're going to see the quadratic factors. So we have a special place where our solutions go. X equals 1/2 works. So now what was your quadratics? What was your quadratic, sir? 2x squared plus 24. Okay, I'm going to factor out of 2. Do you agree?
Yeah.
So factor out of 2, then we get x squared plus 7x plus 12. Let's see if that factors. What multiplies to be 12 and adds up to be 7? 4 times 3?
Yeah.
What the? Somebody said 4 and 3 didn't work. They did synthetic division, but isn't it going to work? Oh no, they're negative. They're going to come out negative, that's why. You're right, they didn't work. So continue factoring. So we factor it, it gets x plus 4, x minus 3. True? Or x plus 3. Aren't those our factors? So what are our other 2 rational roots? Negative 4 and negative 3. So that was way quicker than continuing testing. Sweet! I like it. That was fun. Which, look, it really did work out. We had 2 negative real roots, and we had 1 positive real root. It all makes sense. Hey, we don't need another example. I truly believe that. Don't do these